This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and the scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form BC, Question 2. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form BC Question 2 involves a particle moving in the plane. Its position is given by a vector-valued function, x of t, y of t, at time t, where t is measured in seconds, and x and y are twice differentiable functions, both measured in meters. We are given a symbolic expression for the derivative x prime of t, and we also have selected values of y prime of t given in the table. And in addition, we know that the position of the particle at time t equal 12 is 4 minus 3. In Part G, we're given values for y double prime of 12 and y triple prime of 12. And we need to find the third-degree Taylor polynomial approximation for y about t equal 12. Now, we could probably spend 2 months talking about Taylor series and Mclaren series, but here's the basic concept needed to solve this problem. It says that if a function f has a power series expansion at a, then it must look like this. This is the Taylor series of the function f centered at a. While I'm here, I want to mention the special case when a is equal to 0. This is called the Mclaren series, and the form of the series is given here. Knowing the general form of a Taylor series, we can solve this problem by assembling all of the right pieces and make sure to use correct notation. A couple of little things here. First, the independent variable in this problem is t. Now, we probably won't penalize a student who uses x instead, and I'll talk a little bit about this later, but I'll try to use t as given in the problem. And since we want a third-degree Taylor polynomial, we'll need values of y, y prime, y double prime, and y triple prime at t equal 12. All right, let's see. Y of 12 is equal to minus 3. This is the y coordinate of the position of the particle at time t equal 12, as given in the statement of the problem. Y prime of 12 is equal to minus 5. This value is taken from the table, also given in the problem. And y double prime of 12 is equal to minus 2. Y triple prime of 12 is equal to 8. Those two values were given in this specific part of the problem. Now we've got all the pieces, let's put the Taylor polynomial together. And I'll name this third-degree Taylor polynomial g of t. The student can use just about any name, except they do have to be careful using y of t and an equal sign. Here's the form of the third-degree Taylor polynomial of the function y centered at 12, using the independent variable t. In this step, I used all of the known values. And then finally, I simplified just a little. Here are the scoring guidelines for Part G. This problem was worth 2 points. The first point is for presenting any two terms of the third-degree Taylor polynomial. And the second point is for the remaining two terms. Here are some interpretations of these scoring guidelines to help understand how points are awarded in this type of a problem, and to help prepare for the next AP Calculus exam. The first point is earned for presenting any two correct terms, and the signs are included as part of these terms. Now, the terms don't need to be simplified, and we'll consider the very first presentation of these two terms. That is, if a student goes on to make a simplification error, then they will not earn the second point. And we'll only consider polynomials centered at t equal 12, or OK, at x equal 12. Unfortunately, if the student reflexively writes the third-degree Mclaren polynomial for y, this will earn no points. The second point is for the correct remaining two terms. It's pretty clear that the student is not eligible for the second point unless they earn the first point. If the student includes terms of degree greater than 3 or adds a plus ... then they do not earn the second point. And again, if they go on to make a simplification error, then they will not earn this second point. It's not necessary, but the student can name this polynomial almost anything they want. But they cannot equate their polynomial to y of t. They can use an approximation symbol, but they cannot write y of t is equal to the third-degree Taylor polynomial. In addition, they cannot equate their polynomial to a constant, like y of 12 or t sub 3 of 12. In part H, we need to use the Taylor polynomial found in part G and set up an expression that represents the total distance traveled by the particle over the time interval 12 to 15 seconds. The key concept here is, of course, the distance traveled by a particle. That is, how to find the distance traveled by a particle over a time interval when the particle is moving in the plane. Now, I'm going to talk about this concept in the context of a vector function. One of the most important definitions in any mathematics class is that of a function. And we know that a function is a rule that assigns to each element in the domain a unique element in the range. A vector-valued function, or just vector function, is simply a function whose domain is a set of real numbers and whose range is a set of vectors. This problem, in my opinion, involves a vector function whose values are two-dimensional vectors. The reason is because there is a close connection between vector functions and particle motion. Suppose a particle moves in the plane so that its position at time t is given by these parametric equations. If we consider the vector function r, then r of t is the position vector of the point P. Therefore, any continuous vector function r describes the motion of a particle in two dimensions, and it also defines a curve c that is traced out by the tip of the moving vector r of t. The derivative r prime of t of a vector function r is defined in much the same way as for a real valued function. As a result, if we write r of t like this, then here's an expression for r prime of t. We simply take the derivative of each component. If a particle moves along a curve so that its position vector at time t is r of t, then the velocity vector v of t is given by this expression. And finally, the distance traveled by the particle from time t equal a to time t equal b is given by this integral expression. If you remember solving problems involving this concept, the resulting integral is often a little tricky. Technology is a great help here. Let's use these concepts to solve this problem. For t between 12 and 15, we're told that y of t is the same as the Taylor polynomial approximation found in part G, which I labeled g of t, strangely enough. Knowing the formula for the distance traveled, I need an expression for dx dt, or x prime of t. And this expression was given in the statement of the problem. And to find dy dt, or y prime of t, I need to take the derivative of my expression for y on the interval 12 to 15, term by term. Finally, I assemble all of these pieces into a definite integral that represents the distance traveled by the particle over the time interval 12 to 15. Yikes! As an aside, do you think you could find an exact symbolic answer here? We might have to settle for a numerical approximation. Here are the scoring guidelines for Part H. This problem was worth 2 points. The first point is for finding a correct expression for y prime of t. And the second point is for putting everything together and writing a correct expression for the distance traveled by the particle. And here are some interpretations of these guidelines. The first point is earned for presenting the correct derivative y prime of t. The student might denote this derivative differently, but in general we're looking for the derivative of their expression from Part G. We will allow the student to import an incorrect third-degree Taylor polynomial about t equal 12, and we'll read with them to determine if they found the correct derivative. And if y prime of t is incorrect, the student is still eligible for the second point. Now, at an actual AP Calculus reading, there would probably be some additional restrictions on the nature of an incorrect import from Part G, because we want to make sure that the complexity of the derivative remains about the same. For example, if the student's third-degree Taylor polynomial was simply a constant, well, then that leads to a much simpler derivative here. The second point is for a correct expression for distance traveled. So this is earned for a correct definite integral. And we have to be careful when reading this presentation. The student must have all the necessary opening and closing parentheses, and the squares in the right places. If the student goes on to make a simplification error, then they will not earn this second point. However, if the student happens to present an answer to this definite integral, analytically or numerically, we will just ignore that part of the presentation. Inevitably, there are issues in a problem like this with the symbol dx used instead of dt. So here's how I would score this. I want the variables in the two derivatives underneath the radical sign to match. Usually they should either both be in x or both in t. I'll ignore the differential in awarding the second point. And even if the dt or the dx is missing, the student can still earn the second point. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts, and a reasonable expectation of how they would be scored. This video concludes BC Free Response Question 2.